So let's talk about spectroscopy. I'm going to go back to my black pen here. Okay. Spectroscopy. Okay. And specifically, this is called emission spectroscopy due to the emission of light of a material. So suppose we have a hydrogen lamp. So believe it or not, we can have a hydrogen lamp. Many of you are familiar with neon lamps. And yes, those are filled with the gas neon. It's not some like trademarked or whatever. A neon light literally has neon in it. So just the same, we can have a hydrogen light as well. And if we pump a bunch of energy into one of these types of lights, these are called gas discharge tubes, then it will glow. And it will glow a characteristic fingerprint, okay, that we call its emission spectrum. So each atom, each molecule has its own unique fingerprint of an emission spectrum, and that's how we can identify what is in certain materials. So for example, now, if we had this glowing gas discharge tube, it would kind of have this pink color, and our eyes are pretty crappy light detectors, so we couldn't tell exactly what colors were coming out of this. It would just look like this overall pink color is kind of there. But now if we were to put this in a prism, which I talked about this, right? In this prism, because there's different densities, so the light wavelengths travel at different speeds, those wavelengths will become separated, just like in the Pink Floyd Dark Side of the Moon picture, right? Let's back up to that. Right, this picture right here, so the refraction, okay? And so, of course, this is showing if you have white light, you'll get all the wavelengths, but instead, rather, if you have light coming from a specific atom or molecule, it will only have those characteristic fingerprint wavelengths of that atom or molecule itself, okay? And for hydrogen, we would see 4 lines in the visible, 410.1, 434.1, 486.1, and 656.3. So all of these together combined to us would look kind of pink because we don't have prisms in our eyes the same way that this does, right? Our eyes can't separate those wavelengths. But a fancy electronic device like a spectrometer could. And thus we would get the fingerprint of that material, okay? So here's what some other fingerprints look like. So again, here's hydrogen. And so as we get to more complicated, bigger atoms, they have more complicated fingerprints. So helium, even though it's just one extra electron, right? We recognize hydrogen as 1 electron and 1 proton. Well, helium has got 2 electrons and 1 proton and 1 neutron, okay? So it gets a little bit more complicated. And you can see that right here. It's got more lines. And in fact, this is actually a helium lamp. Someone very creatively made these glass-blown tubes, filled them with these elements, and then discharged them with a high power source so that you can see what it looks like, but then a spectrometer shows you all of those wavelengths. And then now, right here's our famous neon lamp. And there's a reason why neon lamps always look kind of red, because you can see the majority of those characteristic fingerprint lines are red. And in fact, you can make some yellow and some green neon lights if you filtered out those red wavelengths. But notice how there's nothing that's blue. So if you've ever seen a blue neon light, it's not neon. It's something else. Neon does not emit any blue light. So it could be a helium light or another atom that emits blue light. But no such thing as a blue neon light. So now you know. Okay, so moving on. So this is how I'm going to start to build this whole idea up of how we get these specific fingerprint wavelengths, okay? And so this idea is kind of based on the Bohr model. And so this idea, I'm going to skip ahead, and what I'll show you with the Bohr model, the idea behind the Bohr model is here is the nucleus in the center. Okay? So that is our protons and neutrons. Okay? And in the Bohr model, electrons exist in these orbits. So I'm going to call these electron orbits. Okay? And these orbits are given by what we call N, principal quantum number. Okay? So I know we use N for number of moles, but we also use it to describe what's called the principal quantum number, which gives us these, that says electric orbits, electron orbits about the nucleus. Okay? So for example, the N equals 1 is the closest orbit to the nucleus. Okay? So we call that the ground state. N equals 1 is the ground state. That's where we expect electrons to exist at room temperature. Under normal conditions, electrons will be in this ground state. Okay? So now look, we've got this N is equal to 2 level right here. Or N is equal to 3 or 4 or 5 or 6, 7, 8, 9, 10. They're whole number integers. Okay? Those are what we call excited states. All right? And so what happens in these excited states is we typically pump energy in. So that's done by that gas discharge, right? So I talked about how, so really, let's see, if I finish drawing this thing, I'm just going to draw this as like a closed circuit, okay? So we're pumping electrons, we're pumping, energy through this thing. We're giving it power. So maybe there's a battery hooked up or it's plugged into the wall or something like that, okay? So energy goes in, and I'll draw that with these arrows. And as it turns out, when energy goes in, it pumps these electrons up to these various excited states. This is part of what we call, this is why we call it quantum mechanics, because quantum, what that really is referring to is that these energies are quantized. So in other words, when these atoms absorb energy, they only absorb specific quantities of energy. They absorb, so I'll say energy in right here. They absorb exactly the energy they need to go up to these various levels. So everything starts at the ground state, but perhaps they might, if there's enough energy to take it all the way up to level 5, that would be a lot of energy. So on this scale, the longer the arrow, the more energy is being absorbed. So it could absorb up to level 4, up to level 3, up to level 2. So we're pumping a bunch of energy, enough energy to populate all of the excited states. So we're pumping electrons into these excited states, putting them into higher energy orbits, okay? And so now these molecules or these atoms, they don't like being in these high energy states, so they relax. And they relax by releasing energy, and that energy is quantized. Okay, so I'm going to draw a purple line right there going from 5 to 2. And now I'm going to draw like a little, let's see, do I have a cyan color? I'll use blue. So I'll draw a blue color going from 4 to 2. Oops. So a blue color going from 4 to 2. And then now I will draw a red color going from 3 to 2. And I'm going to draw, let's see, what color haven't I used? I need a different purple color. So I'm just going to use another black, and I'm going to make it dotted. And then, oops. So, and I'll explain why I chose specifically all of those colors. Let's go with like a gray, okay? And I'm just going to show that one going all the way down, okay? So there become all of these different combinations of energy relaxation. So that's now energy out, okay? I don't know why I drew a box right there, so we'll have to deal with that. So all of those arrows refer to energy out. Well, hopefully you can see where this is going, okay? Because as it turns out, this line here at 434 is related from going from level 5 to level 2. And this is specific for hydrogen. So other atoms will have different spacings in their energy levels and thus give you a different fingerprint. Okay. So going from 4 to 2 gives you this 486 line, this kind of cyan blue line, okay? And going from 3 to 2 gives you this red line, okay? And so I'll remind you that this is the biggest energy, so I'll write high energy up here and low energy up here. And you can see that's why 3 to 2, from level 3 to level 2, only gives you a red light because red is lower in energy than blue. So that 4 to 2, that's a bigger arrow, that's a bigger energy gap, so that requires more energy, okay? So now what about level 2 to 1? Well, as it turns out, level 2 to 1 is ultraviolet. So that's such a big gap. And remember, the size of the arrow on this diagram indicates how much energy there is. So as it turns out, level 2 to level 1 has the biggest gap, and that's true for all things. So it actually gives you ultraviolet in the case of hydrogen. But now, once again, this 3 to 2 gives you that red line, this 4 to 2 gives you that blue line, and this 5 to 2 gives you that purple line, okay? And so that's kind of being showed to you here on this Bohr model with all of these indicated lines, right? From 5 to 2, from 4 to 2, and from 3 to 2. And certainly from 2 to 1 exists, that happens, but we wouldn't be able to see that visibly with our eyes because it's ultraviolet, okay? So now this is the equation that we use here. So this is our Rydberg equation, and that says delta En, and what that means is the difference in energy level, because as it turns out, it is the difference, the delta, right? So we recognize delta En is going to be E in final minus E in initial. The difference between those two energy levels is what gives us light. It's what gives us that characteristic fingerprint, okay? So let's do an